Hi everyone. Now we will see quick revision from photochemistry topic. What are the various important equations, conclusions, those things we will discuss in the last time 7 questions given from photochemistry and right. So first photochemistry deals with what? Photochemistry deals with what? Various process that occur by absorption of light energy. Various process means it may be a physical process or a chemical process. Physical or chemical process that occur by absorption of light energy. And for example, we are taking reactant molecule, for example, M, we have to apply light energy. So which region we use and in photochemistry UV visible radiation we use. What about wavelength range and 200 to 400 for UV 400 nanometers, and for visible 400 nanometers to what 700 or 800 nanometers and 700 or 800 nanometers. In angstroms 2000 to 4000 angstroms and UV visible range is 2000 to 4000 angstroms. Okay, so we may apply UV visible radiation. Whenever we are applying UV visible radiation, what happens? And electronic transitions occur. And ET means what here? Electronic transitions occur. So molecule goes to higher energy level. And so from that it may participate in the reaction. That excited state molecule may participate in the reaction. It may overcome energy barrier and may participate in the reaction. Okay. So before going to photochemistry, if you see some of the differences between thermal reactions and photochemical reactions, and what are the differences between thermal reactions and photochemical reactions? Here, what about energy source? And energy source is what here? Heat. Here, what is the energy source? And light. Here activation energy required is given in the form of heat. Here activation energy required is given in the form of light. So therefore here as temperature increases, rate also increases. But here rate is independent of temperature, but it depends on what? Light intensity. And if intensity of light increases, okay, rate also increases. Next, these are what? Non-selective reactions. But photochemical reactions are said to be what? Selective reactions. And when thermal reactions may occur spontaneously, and if delta G is less than 0, these are also said to be what? Dark reactions. Light energy may not required. Heat energy is required. Dark reactions. Delta G is less than 0, but here no such conditionally. Either delta G may be less than 0 or greater than 0 for a photochemical reactions. These are some differences between thermal and photochemical reactions. Okay. Next one, what are the various fields where we use photochemistry? And photochemistry is involved in the synthesis of vitamin D. In the synthesis of vitamin D, photochemistry is involved or not? Yes. In the synthesis of vitamin D, right? Next one, in various polymer industries, in medicinal and laser technology. This laser technology we follow for high surgeries. For in cancer treatment, we use this laser technology, right? We have various fluorescent and phosphorescent substances. We use fluorescent substances um, to know fake notes, and to know fake notes, we can use fluorescence and fake notes. Next, in LED and light emitting dividers, TV screens, in various cases we use fluorescent substances. And right, in fluorescent spectroscopy we have, in analysis we follow what? Fluorescent spectroscopy. We have phosphorescent substances. Phosphorescent substances, those we use in glow in dark materials, and glow in dark materials, that is clock dials, okay, wristwatches, paints, safety signs, in safety boards, and night time in safety boards. Okay, these phosphorescent materials are useful. And in solar cells or photovoltaic cells, Solar cells are photovoltaic cells. Which energy converted to which energy? And light energy converted to what? Electrical energy, right? We may use amorphous silicon or PN junction diodes. In solar cells or photovoltaic cells, we may use amorphous silicon or PN junction diodes to convert light energy to electrical energy. We know in photosynthesis, okay, light energy converted to what? Uh, carbohydrates. Carbohydrates. Chemical energy and light energy converted to what? Chemical energy and chemical energy. In the presence of what? Chlorophyll. What is the role of chlorophyll and that acts as what? Sensitizer. Sensitizer. What are the examples for sensitizers and some examples for sensitizers? If you see uranyl sulfate, chlorophyll, most widely you may use benzophenone, organic photochemistry, benzophenone, sodium, mercury, iodine vapors we can use as sensitizer and right. In photosynthesis totally 48 photons are absorbed and 6 CO2 plus 6 H2O. Okay, 48 photons are absorbed to give carbohydrates. So for each 1 mole of reactant, 8 photons is absorbed. Okay. So various photochemical reactions we may carry out by using light energy and various photochemical reactions we can carry out by using light energy. This is useful in polymer industry also, etc. Like this, we have various applications of photochemistry. We have only right. Next one, we know energy of one photon is given by what? Energy of one photon or quantum. Energy of one photon or quantum. Energy of one photon or quantum is given by what? H nu or hc by lambda or hc nu bar d, right? That is the expression for energy of photon or quantum. Next one, energy of Einstein and Einstein means what? Avogadro number of photons energy is called 1 Einstein. So that is what? NaH nu, Avogadro number of photons energy adding. So various formulas for Einstein energy, if you see, 119.7 into 10 power 6 by lambda in centimeters. This is in ergs and ergs. If you want to in joules, we will get 11.97 by lambda in centimeters, that we will get in joules only. If you want in kilojoules, 11.97 into 10 power minus 5 lambda we have to substitute in meters and that we will get in kilojoules. If you want in calories and 2.86 by lambda in centimeters, that we will get in calories and so these are the various expressions for Einstein energy. That is nothing but what? Avogadro number of photons energy is called Einstein energy. And okay, next one, various laws of photochemistry. So in that first one is Grotthuss Draper law. Grotthuss Draper law. According to Grotthuss Draper law, what happens? And only absorbed radiation gives changes in the system. And absorbed radiation causes changes in the system. Unabsorbed radiation doesn't lead to any changes in the system. That is called Grotthuss Draper law simply. Next, what about Stark-Einstein's law of photochemical equivalence and Stark-Einstein law of photochemical equivalence. According to this law, there exists a 1:1 relationship between number of molecules adsorbed and number of photons, number of molecules participated and number of photons absorbed, or number of moles participated and number of Einsteins absorbed. So each molecule participating absorbs only one photon only, or each mole of reactants participated in the reaction absorbs one Einstein only. So that is called Stark-Einstein's law of photochemical equivalence only. So next one, Lambert's-Beer's law. According to Lambert's-Beer's law, absorbance is given by or optical density. Small difference is there. Both are almost the same. Absorbance or optical density is equal to what we have only absorbance or optical density is equal to various expressions. If you see, log I naught by IT or minus log T, where T is called what? Transmittance. And transmittance, that is nothing but fraction of light transmitted, and fraction of light transmitted, IT by I naught, and that's why we get minus sign, or percentage of transmitted, and 2 minus log percentage of transmittance. And another expression is what? Epsilon CL. And so these are the various expressions we have for absorbance. And A2 by A1 we can write as what? C2L2 by C1L1. And okay, if you take a mixture of two solutions, and total absorbance is given as absorbance of first solution plus absorbance of second one. And okay. So absorbance depends on what? C and L, path length and concentration. Path length and concentration. Epsilon is called what? Molar extinction coefficient. What about unit for optical density or absorbance? And no unit. And no unit. What about epsilon? And epsilon unit is A by CL, M inverse centimeter inverse. And molarity we can write as moles per liter or moles per decimeter cube. That is the unit for epsilon. Epsilon is the characteristic of given substance. How strongly a given wavelength radiation is absorbed by a given substance, that is given by epsilon. And molar extinction coefficient or molar absorption coefficient or absorptivity, and that is also called as absorptivity. And okay, so absorbance depends on what? Concentration, and L is called path length or cuvette length or cell length. And so in this is IT by naught is called what? Fraction of transmitted radiation. So fraction of transmitted radiation or transmittance is given by IT by naught is given as, okay, with respect to epsilon CL. Log T is equal to what? Minus epsilon CL. So T is equal to what? We get 10 power minus epsilon CL. And so this is what? Transmittance or fraction of radiation transmitted. And now fraction of radiation absorbed is what? 1 minus 10 power minus epsilon CL. Okay, if IA is the I naught is the intensity of incident radiation, IA is intensity of absorbed radiation, IT is the intensity of transmitted radiation. What is the relation between these three? And IA is equal to what? IA plus I naught is equal to what? IA plus IT. And incident radiation is equal to 100 photons, for example. In that 75 photons are absorbed, 25 photons are transmitted. And 100 is equal to 75 plus 25. Again, we'll get 100. I naught is equal to IA plus IT. And so fraction of transmitted radiation is what? IT by I naught. And fraction of absorbed radiation is what? IA by I naught. And IA by I naught. If you add these two, what will get? And 1 we will get always. FA plus FT value is 1. And right. So this is about Lambert's Beer's law. And so most path length will be taken as 1 centimeter and 1 unit. And so epsilon absorbance is equal to epsilon C. This is in the form of y is equal to mx. So we will get a straight line passing through the origin. From that we can determine what? Unknown solution concentration we can determine. And what are the limitations in the Lambert's Beer's law? What are the limitations? Two questions given in the last time from Lambert's Beer's law. One question is absorbance depends on epsilon, C, L and color. Epsilon doesn't depend on which of the following options: epsilon, C, L and color. And color doesn't depend on color. What are the limitations in the Lambert's Beer's law? It is applicable to which solutions? And only dilute solutions. If we take concentrated solutions, what we have? And ion-ion interactions we may have. Ion association may take place. Ion dissociation may take place. Ionic solutions. Ion-ion interactions are present, then we may get deviations. And if ion association and ion dissociations are present, then we may get deviations from Beer's law. Next, temperature also remains same. And okay, particularly for the reactions involving ions, as temperature increases, what observed? And bathochromic shift is observed. And bathochromic shift, absorbance bands shift towards higher wavelengths. And absorbance bands shift towards higher wavelengths. So temperature should be maintained constant. Mostly we may maintain constant temperature. And okay, Next, refractive index also not to be changed, and if you take concentrated solution, refractive index changes, and in such cases also light refractive index may changes. In such case also we may get deviations, and we have to take what? Homogeneous solution. We have to take what? Homogeneous solution. Uniform concentration we have to take, and right. Mm, these are some of the limitations, and main one more thing, and important things are, one is a dilute solution we have to take, another one is monochromatic radiation we have to apply, and single wavelength radiation we have to apply. Monochromatic radiation or single wavelength radiation we have to apply, and okay, once you listen these points, and okay, whatever the points are not known to us, okay, those points you may note, and right, almost all the points will be covered, and mostly, right. This is about Lambert's law and limitations in the Lambert's law. Next one, electronic transitions. If you see electronic transitions, various possible electronic transitions are what? Sigma bond possess most stable one. Sigma bonding molecular orbital possess least energy. Next one, pi bonding molecular orbital. Next, non-bonding orbital. Next, pi star. Next, sigma star. Anti-bonding molecular orbitals possess higher energy. Bonding molecular orbitals possess lower energy. So sigma to sigma star is allowed, and so that is according to symmetry rule, and gerade to ungerade is allowed, and symmetry rule, that is symmetry rule, and pi to pi star is allowed, and pi is ungerade, and pi bond, pi star is what? Gerade, and ungerade to gerade or gerade to ungerade is allowed transition, and okay. Next, some more possible transitions. If you see n2 sigma star and n2 pi star, and what about order of energy, and sigma to sigma star is more highest energy gap we have. So order of energy absorbed, and wavelength we will get reverse, and energy is inversely proportional to wavelength. So wavelength will get reverse order. So next one, n2 sigma star, y2 pi star. Least energy gap is there for N2 pi star transition. Energy absorbed is very small, and your energy gap is high. So generally this type of transitions observed in saturated compounds and having sigma bonds, and that means alkanes, cycloalkanes shows this type of transitions, and N2 sigma star non-bonding electrons and sigma bonds, and that is mm, compounds having oxygen, nitrogen, sulfur, halogens, and halogens. For example, alcohols, ethers, thioethers, amines. In such compounds, we can observe N2 sigma star type of transitions, and pi to pi star unsaturated compounds, and alkenes, aromatic compounds, for example, benzene, etc. N2 pi star carbonyl compounds, aldehydes, acetones. Next one, nitro compounds. Next is cyanide. Okay, nitro compound, cyanide. Those compounds we may observe N2 pi star type of transition cell. So by absorption of light energy, U visible radiation, what happens? These electronic transitions may be observed, and okay, generally gerade to ungerade is allowed, and according to selection rules. Ungerade to gerade also allowed according to selection rules. That is called symmetry rule or parity or Laporte rule. Okay. Next one, what is the time required for electronic transition? And time required for electronic transition is okay 10 power minus 15 seconds, and this is also called as what? Femtoseconds, and femtoseconds. And the time required for vibrational transition is 10 power minus 13 seconds, and that means here time required is 100 times more. So vibrational transitions are slow compared to electronic transitions. That's why during electronic transitions, no vibrational motions, no change in the geometry, or no change in the relative positions of nuclei. So during electronic transitions, geometry is not changed, and or no change in the relative positions of nucleus, and no change in the relative positions of nuclei. So no change, and this is called what? Frank-Condon principle, and that is called as Frank-Condon principle. And according to Frank-Condon principle, electronic transitions are called as what? Vertical transitions, since no change in the bond distance and relative Okay, what bond length and or no change in the internuclear distance and as no change in the internuclear distance, no change in the internuclear distance, so electron transitions also are also called as vertical transitions, and this is about Frank Condon principle and okay. Next one, M molecule, it absorbs UV visible radiation, electronic transitions occurs, and we are getting electronically excited molecule. We are getting electronically excited molecule. So it may be what singlet state or triplet state and based on what spin multiplicity and for example unpaired opposite orientation is there and parallel anti-parallel orientation is there, anti-parallel orientation is there, total spin is plus of minus of 0 will get, so therefore spin multiplicity is given by what 2 into mod s plus 1 and so 1 j is equal to 1, such state is called singlet state and triplet state means what parallel orientation and parallel orientation, in this case s is equal to will get either plus 1 or minus 1, total electron spin and plus of plus of plus 1 minus of minus of minus 1, so j is equal to what will get in 2 into 1 plus 1, that is 3, and if j value spin multiplicity is 3, spin multiplicity is 1, that is called singlet state, spin multiplicity is 3, that is called triplet state and okay. Mostly in the ground state, which state is possible and singlet state is possible, most of the molecules possess paired electrons and paired electrons, most of the molecules possess paired electrons in the ground state, so therefore we will get singlet ground state and for oxygen molecule, but we get triplet state in the ground state. Okay, next we may get various excited states like this and singlet excited states. Okay, next one corresponding triplet excited states and right. One more selection rule is what spin multiplicity rule and spin multiplicity rule. According to spin multiplicity rule, singlet to singlet is allowed, triplet to triplet is allowed, but singlet to triplet not allowed, triplet to singlet is not allowed. Okay, so that means S0 to T1 is allowed or not allowed, and such transition is not allowed. And so S0 to T1 cannot occur directly and cannot occur directly and okay, such transition cannot occur directly and right. And according to Hund's rule, always energy of triplet state is less than corresponding singlet state and so energy of T2 is less than what energy of S2 and always energy of triplet state is less than corresponding singlet state and according to Hund's rule of maximum spin multiplicity. As spin multiplicity increases, energy decreases and for example by the absorption of light energy it goes to excited state like this and okay, excited state like this. Now okay, okay, M plus H nu gives M star and this is excited molecule. Here initially we are taking M and ground state molecule. This excited molecule we are indicating as M star. This is unstable and okay, it may comes to ground state by releasing its excess energy in the form of heat or by releasing its excess energy in the form of light, or it may participate in a photochemical reaction and it may participate in a reaction that is called photochemical reaction. If it gives its excess energy in the form of heat and comes to ground state, okay, ground state again comes to ground state, this is called as non-radiative process and non-radiative process or radiationless process, this is called what radiative process. And if it comes to ground state, if by losing excess energy in the form of heat, non-radiative process, by losing excess energy in the form of light, radiative process, if it participates in a reaction that is called photochemical reaction. Okay, and again non-radiative process are of two types and non-radiative process are two types, internal conversion and intersystem crossing and radiative process are also two types, that is fluorescence and phosphorescence and fluorescence and phosphorescence. right? This diagram is called what as Jablonski diagram, and Jablonski diagram gives all photophysical processes, and so all these four are called as what? Photophysical processes, and all these four are called what? Photophysical processes. Since here they are not involving a chemical reaction, and so all those four are called as photophysical processes, and okay. For example, the molecule goes from higher second S2 state to S1 state by releasing excess energy in the form of heat, and for example, non-radiative process I am indicating by wavy arrow, and wavy arrow. Radiative process I am indicating by straight arrow, and so wavy arrow indicates what? Non-radiative process. That means excess energy released in the form of heat, and excess energy released in the form of heat. This is called as internal conversion, and is there any change in the spin or no change in the spin, and no change in the spin, that is called internal conversion, and for example, S2 to T2, okay, excess energy released in the form of heat, and this is called as intersystem crossing, and intersystem crossing. That means spin multiplicity is changes, and singlet to triplet spin multiplicity changes, and next one, straight arrow. Straight arrow means radiative process. Okay, in between same states, and in between same states is called fluorescence, and in between different states that is called as phosphorescence, and in between same states is called fluorescence, in between different states is called phosphorescence. Okay, so that means in fluorescence and internal conversion, if you observe fluorescence and internal conversion, no change in spin multiplicity, and J is not changing and spin multiplicity is not changing. So generally these two are fast process, and whereas phosphorescence and intersystem crossing, these two are slow process. J value is changing, spin inversion is occurring. Spin inversion is occurring either singlet to triplet or triplet to singlet. So they are said to be what? Slow process, and okay, if triplet to singlet occurs, and that is called reverse intersystem crossing, and that is called reverse intersystem crossing, and next one, in between electronic energy levels, what we have? And vibrational energy levels we have. So from higher vibrational energy level to lower vibrational energy level, that is called as vibrational relaxation, and that is also a photophysical process. Higher vibrational energy level to lower vibrational energy level, that is called vibrational relaxation, and so all photophysical process represented in the form of a diagram that is called Jablonski diagram, and okay. In addition to photophysical process, if you give energies, lifetimes, kinetics, kinetic data, all those if you give, that is called state diagram. State diagram means energy of singlet state, energy of triplet states. What about lifetimes in singlet state? S naught, sorry, S1 lifetime, S2 lifetime, T1 lifetime, T2 lifetimes, rate constants for the process occurring from those states. If all such data also given, that is called what? State diagram. Okay. Next one, some more points if you see regarding fluorescence and phosphorescence, and the substances which shows fluorescence phenomena is called fluorescent substances. The substances which shows phosphorescence phenomena are called phosphorescent substances. Okay, both comes under photoluminescence, and both comes under photoluminescence. Okay, this also comes under photoluminescence, and that means they emit light energy by the absorption of light energy only. Okay, we are applying light energy, we are irradiating light energy, external light source on phosphorescent substance or fluorescent substance, and again they also emit light energy. The excess energy is released in the form of light. So those are called photoluminescence, and for example, by chemical reactions, and by chemical reactions, if light energy is evolved, that is called chemiluminescence, and chemiluminescence by chemical reactions, and okay, bioluminescence is an example for what? Chemiluminescence, and bioluminescence is an example for chemiluminescence, and so this is observed in the case of glowworms, fireflies, certain shark fishes. Okay, here if, if light energy is released due to chemical reactions, and that is called chemiluminescence. If it is observed in living organisms, and if it is observed in living organisms, that is called bioluminescence, and bioluminescence comes under chemiluminescence only. Glowworms, fireflies. In this luciferase, an enzyme is present. Because of that enzyme, okay, here light energy is emitted, and okay, so here we are not applying light energy, and because of chemical reactions light energy is emitted. So these are said to be what, chemiluminescence and bioluminescence, and those comes under. Some of the differences, if you see fluorescence and phosphorescence, both comes under photoluminescence. It is instantaneous process and fast process. As soon as external energy, okay, external energy is cut off, okay, fluorescence process is also stopped, and but it is a slow process. It is also referred as slow fluorescence. Even after cut off external light, the emission of light is observed from phosphorescent substances up to some minutes, some hours, and that's why these are used in glowing dark materials, wristwatches, clock dials, safety signs, paints. Okay, in those we can use phosphorescent substances, and in both the cases generally wavelength of radiation emitted is greater than, okay, energy emitted is less than absorbed radiation. So wavelength is more than absorbed radiation in both the cases, and since this is the energy absorbed, and this is the energy absorbed, but this is the energy evolved, and in fluorescence and phosphorescence phenomena, so energy absorbed is high but energy released is small, and small energy means wavelength is high, and so wavelength of light emitted is more compared to absorbed in both the cases, and some examples if you see for fluorescent and phosphorescence phenomena, and for fluorescence phenomena examples if you see, you may remember, that is fluorescene, fluorescene, eosine, quinine sulfate, rhodamin B అంట, rhodamin B, just ఒకసారి చదివి వదిలేయండి, rhodamin B. Okay, these are some examples for fluorescent substances, and okay, examples for phosphorescent substances if you see zinc sulfide, some heavy metal sulfides, strontium aluminate, strontium aluminate, right? These are some examples for phosphorescent substances, and these are some examples for fluorescence and phosphorescent substances. Uranyl sulfate also example for fluorescent substance. Chlorophyll also an example for fluorescent substances, and right. Right, this is about various photophysical processes, and various photophysical processes. Next one, photochemical processes, and in photochemical process, okay, right, the excess energy may not released in the form of heat or light, but excited molecules may undergo further chemical reaction and give products, and the various examples if you see photo oxidation, okay, photo oxygenation, okay, anyhow photo oxygenation comes under photo oxidation only. Here oxidation means not only addition of oxygen, and removal of electrons or removal of hydrogen also comes under photo oxidation, and but photo oxygenation means compulsory you have to add oxygen only, and that is the small difference, and so photo oxygenation comes under photo oxidation only. Photo addition, photo addition, photo dissociation. So the various examples for photochemical process, and photo isomerization, photo reduction, Okay, photo addition, photo dissociation, photo halogenation. Last time this question was given in PCB and photo halogenation, direct question given and right. Like this, we have various photochemical process and for example, photo oxidation RH plus O2 gives rise to peroxides and ROOH will get a peroxide and this is used in rancidity of this is observed in rancidity of oils and rancidity of oils. If oils are exposed to light energy, okay, they undergo oxidation and oils undergo oxidation. Fatty acids are converted to some volatile gases. Okay, some bad smell we may observe from oil and that is due to what? Oxidation of oil. Fatty acids converted to what? Some volatile gases and right. That is called rancidity of oil and in which photo oxidation is involved. Photo oxygenation, for example, anthracene. Anthracene plus oxygen gives what? Anthracene peroxide and anthracene peroxide we will get. Photo addition and for example, two molecules of butadiene, ethylene undergoes addition to give what? Cyclobutane. Cyclobutane that comes under what? Photo addition. Photo dissociation Cl2 gives two Cl molecules or Br2, H2Br2 reaction undergoes what? Photo dissociation. Isomerization and cis-2-butene under photochemical conditions converted to what? Trans-2-butene under photochemical conditions and photo reduction. Reduction of silver bromide, for example, 2Ag plus Br2. This is useful in which industry and photography and this reaction is useful in photography and photohalogenation, for example, CH4 plus Cl2. This question given in the last time. CH3Cl. Hydrogen is replaced by chlorine and hydrogen is replaced by what? Chlorine. So these are some simple examples I have given for photochemical processes. Okay, mostly this type of questions you may expect from what? Organic photochemistry only. So from physical chemistry, you may expect questions based on what? Laws of photochemistry, quantum yield, next singlet triplet states, photophysical process, internal conversion, intersystem crossing. From that we may expect it, right? And lastly, we have quantum yield and quantum yield. How to give quantum yield and for a reaction? Quantum yield is nothing but number of molecules reacted. Number of molecules reacted by what? Number of photons absorbed and number of photons absorbed. Or if you take moles and number of moles reacted, to convert number of moles to number of molecules, we have to multiply with what? Avogadro number. Okay, number of Einsteins absorbed. Number of Einsteins absorbed. This is the formula for what? Quantum yield of a reaction and how efficiently, okay, by the absorption of light energy, reactant molecules are converted to product. That is given by quantum yield. Here we have high quantum yield reactions and low quantum yield reactions. Okay. Generally, if you see photochemical reactions involve two steps and photochemical reactions involve what? Two steps and one is primary process, another one is secondary process and primary process. This is also called as a light absorption step and okay, light absorption step. In the first step, what happens is light energy is absorbed and light energy absorbed, and we may observe two changes and in the primary process mainly two changes. One is excitation and this is called what? Excitation. Excited molecule we may get and otherwise decomposition and otherwise what? Dissociation. By the absorption of light energy, we may observe mainly two types of changes and one is excitation, another one is what? Dissociation. One is excitation, another one is dissociation. Mostly it may follow Stark Einstein's law of photochemical equations. Stark-Einstein's law. That means one molecule participating absorbs one photon, and each molecule participating absorbs one photon. And okay, so light absorption step, and so it involves light energy, and but further subsequent steps light energy may not required, and for further subsequent steps light energy may not required. Those are called as secondary process. Secondary processes, these are generally dark reactions, and here light energy absorption may not required. Those are said to be dark reactions. They are subsequent reactions to primary process. And okay, here why we may get low quantum yield, if you see in secondary process generally may involve one step or more than one step. Secondary process may involve more one step or more than one step. Okay, low quantum yield why we get, if you see, one is various reasons. One is a deactivation, and deactivation, whatever the excited molecule we are getting, again it returns to ground state by releasing excess energy in the form of heat or light. And no involvement in a photochemical reaction, and not involving in a photochemical reaction. Okay, photophysical process occurring. Deactivation or recombination, and recombination, for example in the first step free radicals are formed, again recombined. And for example chain termination step under 2Cl combined, chlorine free radicals combined to give Cl2. So because of this we may get less quantum yield, less amount of product may be formed. Product itself involved in the reaction, and product involved in the reaction, and product may participate in the reaction. This is observed in the case of H2Br2 reaction, and I will explain. H2Br2 reaction. Next one, side reactions, and sometimes side reactions may be observed. Side reactions, and that means M plus H nu gives rise to M star. It has to participate in this reaction to give product, and but instead of this main reaction, some side reaction, some Q is there. Q is called quencher, and some impurity quencher is there. So then what happens, and M plus Q star we are getting. This process is called what? Quenching, and quenching. So actually M star has to participate in the reaction, but due to quencher present, instead of participating in the reaction, it de-excited, and that is called what? Quenching. And so various regions are deactivation, recombination, product involves in the reaction, side reactions, and activation energy may not sufficient. And energy may be less than energy required. And so whatever the energy we supplied, that may be less than the energy required to cross energy barrier. And so in such case also they may not cross the energy barrier, so reactants may not convert it to products. So these are the various reasons we have for getting low quantum yield. And example is H2Br2 reaction. And so if you see the mechanism of H2Br2 reaction, Br2 undergoes decomposition to give 2Br. So this is the mechanism of H2Br2 reaction. Okay. Similarly, if you see the mechanism of H2Cl2 reaction, what is the mechanism of H2Cl2 reaction? So this is the mechanism of H2Cl2 reaction. This is an example for low quantum yield reaction, and that is an example for high quantum yield reaction. Why? If you see, its quantum yield is around 0.01. This is the mechanism we have, right? This is called what? Chain initiator. Here free radical is produced that will initiate chain reaction. These two steps occur repeatedly in cyclic manner. So these are called what? Chain propagation steps, and this is called what? Chain termination step. Okay. So here if you see, observe, second step is what? If you see here, it is exothermic and second step is what? Exothermic and but in this case second step is what? Endothermic and as it is endothermic, it occurs slowly and second step occurs slowly, right? And reverse of second step, and see here, reverse of second step, that is exothermic, so reverse step also occurs, and where HBr is destroyed or not, HBr amount decreases and product amount decreases, and product undergoes in the involvement in the reaction, and product is consumed, and product is consumed, and that's why here we'll get less quantum yield, there we'll get more quantum yield. The main reason is this is like endothermic reaction, second step, here second step is exothermic reaction. So reverse reaction is exothermic. So reverse reaction also occur where HBr is consuming and so if this is an example for what? High quantum yield reaction, and its quantum yield is in the range of 10 power 4 to 10 power 6 and so by the absorption of one photon, 10 power 4 to 10 power 6 reactant molecules participate in the reaction, and chain reactions are involved, and their chain reactions are and formation of free radicals are there, that's why generally their quantum yield is very high end. Okay, and if you see decomposition of hydrogen iodide, and okay, this question given previously in AP set exam, what about its quantum yield? If you see 2 and simple integer we will get, simple integer we will get, so this is the mechanism, and Hi plus H nu gives H plus I, H plus Hi, H2 plus I, so I and I combined to give I2 and right, this is the simple mechanism we have. So by the absorption of one photon, two hydrogen iodide molecules are participating in the reaction, that's why its quantum yield is 2 only. Okay, only one photon is observed but two hydrogen iodide molecules participate in the reaction, so its quantum yield is 2, right? So these are the headings mentioned in your syllabus, and right, photochemistry deals with what we discussed, which region we use, what are the differences between thermal and photochemical reactions. Next one, what is one photon energy, Einstein energy. Okay, next one, various laws, Grotthuss Draper law. Next one, Stark Einstein's law. Next one, Lambert Spear's law. Next, singlet and triplet states, internal conversion, intersystem crossing, various photophysical process. Where I explained by taking Jablonski diagram. Okay, next we have some simple examples I have given for photochemical process. What are the examples for fluorescence and phosphorescence substances? Photosensitization, photo quenching I explained. Next, photoluminescence, chemiluminescence, bioluminescence also I explained. Okay, and finally quantum yield we discussed. What are the reasons for low quantum yield and high quantum yield? Right. So almost all the topics mentioned your syllabus we discussed, and mostly we discussed within 50 minutes, right? Mostly these points are enough, and after verifying these points, you may practice as many questions as possible, and almost I provided 100 questions from photochemistry, and so if you practice those questions, automatically you will get grip on all these points, and right. Thank you.